Consider the following situation. An air compressor draws air at 100 kPa and a temperature of 290 Kelvin through a 0.1 meter squared inlet with a velocity of 6 meters per second into the system. The air then exits the compressor with a pressure of 700 kPa and temperature of 450 Kelvin with a velocity of 2 meters per second. This compressor rejects heat to the surroundings at a rate of 180 kilojoule per minute. We want to calculate the necessary work input into our system in kilowatts. We begin by writing our state variables. At state 1, we have a pressure of 100 kPa and a temperature of 290 Kelvin. Our cross-sectional flow area is 0.1 meters squared and our inlet velocity is 6 meters per second. At state 2, our pressure has increased to 700 kPa and our temperature has increased to 450 Kelvin. Our outlet velocity is 2 meters per second. We begin by writing our conservation of energy equation for a single stream steady state device. Our time rate of change of energy within our system is equal to 0, which is equal to Q dot less W dot plus our mass flow rate into our system carrying an enthalpy, kinetic, and potential energy, less our mass flow rate out of our system carrying an enthalpy, kinetic, and potential energy. If we neglect the change of our potential energies within our system and recognize m dot 1 is equal to m dot 2, we can re-express our conservation of energy equation for our work, such that W dot is equal to Q dot plus m dot times the quantities h1 was h2 plus v1 squared minus v2 squared over 2. We have to determine our enthalpies at state 1 and state 2. We are given our velocities at state 1 and state 2. And we also have to determine our mass flow rate. Our mass flow rate can be found by recalling our definition of m dot and the ideal gas law. Our mass flow rate is equal to our density times cross-sectional flow area times velocity. We evaluate it at our inlet, we'll re-express this as our cross-sectional flow area times velocity per our specific volume evaluated at state 1. Recall for the ideal gas law, P times our specific volume is equal to our gas constant times temperature, and we can substitute in RT per P for our specific volume, such that m dot becomes our cross-sectional flow area times velocity times pressure over our gas constant times temperature. Substituting in our values of 0.1 meters squared for our cross-sectional flow area, 6 meters per second for our velocity, 100 kPa for our pressure, 0.287 kilojoule per kg for a gas constant, and 290 Kelvin for our temperature, we have a mass flow rate of 0.72 kilograms per second. Now, all we have left to find are our enthalpies. Using table A71 on page 762 of our steam tables, the enthalpies at state 1 and state 2 can be found. At state 1, we have a temperature entry of 290 Kelvin, thus our enthalpy at state 1 is directly found as 290.43 kilojoule per kg. At state 2, we have to interpolate for our enthalpy value such that we take our temperature bounds of 440 and 460 Kelvin and the respective enthalpy values at those temperatures to get an enthalpy of 452.14 kilojoule per kg. Now we can substitute all our known values into our conservation of energy equation. W dot is equal to Q dot, and since this heat is being rejected from our system to our surroundings, we have a negative sign of 180 kilojoule per minute, and we have to convert this to kilojoule per second by dividing by 60, plus our mass flow rate, 0.72 kilograms per second, times the following quantities. Our difference of enthalpies between state 1 and state 2, i.e. 290.43, less 452.14 kilojoule per kg, plus the difference of our kinetic energy contributions, v1 squared less v2 squared over 2. Our velocity at state 1 is 6 meters per second. Our velocity at state 2 is 2 meters per second. And recall we have to convert our meter squared per second squared to kilojoule per kg by dividing by 1,000. We can then calculate W dot as negative 119.42 kilowatts, where the negative sign indicates that this work has to be supplied to our system for our compressor to function as described.